Hello and welcome to lecture 34 of Math 2R03. In today's lecture, we're going to be looking at what are called positive operators. And kind of before we dive into that, I just want to kind of give you a heads up for like lectures 34, 35, and 36. So these are the last three lectures of Math 2R03. And we're looking at the final chapter that we'll be looking at, which is chapter 7. Now there's important stuff in chapter 7, but the mathematics is pretty rich and deep. And so if you don't get it all, that's fine. What I want to kind of give you is kind of the broad strokes of what's happening. And we won't go through all the proofs and the details. So just kind of go with the flow, try to get as much out of it as you can. And what's important is that you know that these terms like positive operators. We'll talk about polar decomposition and we'll talk about singular value decomposition. Some of these things you may have seen in other courses, and like what's important is that you know that the stuff is talked about in this book and that if you need this as a future reference, this is a good place to come to. So I'll try my best to explain why these things are important. And you can take a look at the book and you can see why, the proofs get a little kind of more hairy. So right now, again, just to reinforce, just kind of go watch the lectures, read the book, and try to get a broad idea of what's going on. Okay. So having said that, let me make myself disappear. And our goal today is kind of look at two operators, positive operators and isometry. So we've been kind of looking at this theme of first looking at inner products, then we've been looking at operators on inner products, then we're looking at special types of operators on inner products like the adjoint, self-adjoint operators, and normal operators. And in today's lecture, we want to talk about what's called a positive operator. So an operator is positive if it's both self-adjoint and it has the property that whenever you take a vector and you apply that vector to your operator or evaluate it at your operator and then take the inner product, you get some sort of positive real number that's greater than or equal to 0. And this is true for all of your vectors in your vector space. And notice that there's no restriction on your field. It could be the real numbers or the complex numbers. Now, one thing that I've been doing, right, is trying to tie this back to something that maybe you've seen earlier, right? So may or may not be something everyone has seen, but let me kind of give you kind of the matrix interpretation. If we were to assume that we're just looking at the real numbers, and if the dimension of our vector space is n, then we know that an operator in this space corresponds to an n by n matrix, okay? Because that's the dimension of our vector space. And being self-adjoint, right, we've talked about this before, because we're looking at the real numbers, that just means that we're looking at a symmetric matrix. Okay, so we're trying to interpret this definition in terms of what it would mean for a matrix. So this part here means we're looking for a square matrix that's symmetric, and now we have to figure out what this part here corresponds to. Okay, and this is where it gets maybe a little bit more difficult. Here we're using just the regular dot product, right? So this is just the normal dot product. That's our inner product on Rn, right? That's what we're using. And this is just saying that this inner product has to be greater than or equal to 0. Okay, but another way of writing this is saying that the vector AV transpose multiplied by the vector V, which is the same thing as the vector T transpose times the transpose of A times V. And because A is symmetric, this is just saying that the vector any vector V, take its transpose times the matrix A times the vector V gives you something that is positive. And you wouldn't have seen this in Math 1B03, but if you've taken Math 2LA3, this is what's called a quadratic form. So if you haven't done 2LA3, that's okay. You can pull out your linear algebra book and there will be a chapter on quadratic forms. So when we're talking about positive operator, what that would mean if you've taken 2LA3 is you're looking at what's called a quadratic operator, or quadratic form, excuse me. Okay, and so here's another way to think about what t is positive is from the matrix point of view. So we would mean that A is symmetric and the quadratic form VTAV is greater than or equal to 0 for all V inside of your vector space. And there's actually a definition, depending upon you've looked at this before or not. This is saying that A is a positive semi-definite matrix. Okay, so you may not have seen the matrix side. If you have, that's great. If you haven't, what we're just looking at is we're looking at an operator that's self-adjoint and satisfies this property on inner products. Okay, but this is kind of what we're trying to generalize on the matrix side, the matrix side. And just let me kind of show you an example of something that's positive. Now, it takes a lot of work to prove something directly from the definition. And I'll run through the details, but after the break, I'll show you a new theorem that would have made this example a lot easier to figure out. Okay, so here, I want to show that this operator that takes the pair x1, x2 to 5x1 minus 2x2, comma 2, and then the second coordinate is minus 2x1 plus 5x2. I want to show that this is a positive operator on R2. And you know how to find the matrix of this with respect to the standard basis. Okay, it doesn't matter which basis you use, and you get this matrix right here. So this is clearly a symmetric matrix. So T is self-adjoint. Okay, so we have the easy part. We know that it's a self-adjoint operator. Okay, and now by the spectral theorem, which is something we proved in, talked about in the last lecture, we can decompose this. And actually, this might have been the matrix we actually did in the last lecture. I can't even remember if we did or not. We can decompose this into this form. Okay, and what we're doing here, let me just write it out. I'll explain what I've done here, is the spectral theorem says that when you have a symmetric matrix, you can find a basis, an orthonormal basis, such that the matrix, that with respect to that basis, you get a diagonal matrix. So this is the diagonal matrix that you would have got from the spectral theorem. And this, we'll call this matrix P. And this matrix over here, because it's an orthonormal basis, is equal to P transpose. Okay, and so we can decompose our matrix or our operator. So we can decompose the matrix associated to the operator in this form. Okay, and you could think of this, what we're doing is decomposing the operator into a kind of the composition of these three operators. Okay, so what does this all have to do with, showing the positivity? Right, so if you're just to plug in the definition directly, right, we want to show that, okay, when we take the inner product of these two things, and we're using the standard inner product here, right, because we're working in R2, we get 5x1 squared minus 4x1 times x2 plus 5, oh, this should have been x2, and that should have been a 2 right there. X2 squared. And what we want to show is that for any values of x1 and x2, that this is a positive number. Okay. Now that's not easy to see that this number is always positive. So what you have to do is you have to do a change of coordinates. You let x1 equal to 1 over root 2 y1 plus 1 over root 2 y2. Let x2 be 1 over root 2 y1 minus 1 over root 2 y2. And these aren't coming from anywhere. These are coming from the columns of this matrix, right? And I know I'm going very fast, but really what I've done is I'm making a change of coordinates. I'm taking the matrix P that I had before, and I'm multiplying it by the vector y1 and y2, and then I can figure out what x1 and x2 are. Okay, so I make the substitution. I'm writing everything in terms of y's. So I replace x1 and x2 with its corresponding y's. So here I'm making the substitution. make the substitution. And when I plug this all in and simplify, I get 3y1 squared plus 7y2 squared. And you can see that this is always greater than or equal to 0. Okay, so that means that this operator here has to be positive because given any x1 and x2, I can find a y1 and a y2 that satisfy this relation, right? Because P is an invertible matrix, so I can find the y1 and y2 to give me the x1, x2, and I take those y1 and y2, plug it in here, and I'm going to get a positive value. Okay, so it's a lot of work just to prove directly from the definition that an operator is positive. When we come back, I'll give you a different way of tackling this problem.